Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
The second speaker will be Takayuki Okatani from Takayuki University. He actually will talk about something very interesting, how to do image analysis for maybe disaster analysis or relief and so on. I think that will be very, very interesting. So you can see that the kind of data analysis can have very profound societal impact. Welcome.
Thank you for nice introduction. My name is Okatani. I'm from Tokyo University, Japan, and this talk is about a very specific topic, which is our project that we have been doing since 2.5 years ago when Earthquake struck Japan. And actually, I'm not sure if my talk fits a theme of this session, because I don't think I'm particularly doing a big data study. But let me start with what happened, reminding you what happened. March 11th, 2011, massive earthquake hit Japan just before 3 o'clock in the afternoon. It was actually the largest known in Japan. But the real problem is not the earthquake. The real problem is caused by the tsunami caused by the earthquake. Actually, it brought a broad range of destruction on the coastline, and it killed almost 20,000 people, including 2,000 to 3,000 people are still missing. And yes, there are a lot of sad and tragic stories, like all family members but father are killed, or both parents are died and only their children survived, or something like that. And there are a lot of people who are still suffering from the aftermath of this natural disaster. And our university is standing in the middle of this damaged area. And actually, our university is fortunately distant from the coastline, so we didn't have a direct damage by the tsunami. But we strongly hope or eager to contribute to those people and to our community. And as a computer vision researcher, I studied the project of historic images of these damaged areas. And actually, our system is nothing special. It's just a reduced size version of Google view car. We put 300 degrees spherical camera on top of a car with a GPS receiver. And one thing I need to mention is we do not use depth sensor like Google car. And partly because simply we didn't have data concentrated sensor when we started this project. And also partly because as a computer vision researcher, I strongly believe that we could do everything with ordinary cameras. And anyway, our system captures a single shot of 3D measured every 2 meters, like the image like this. And we covered most of the damaged areas, ranging from north to south, almost 500 kilometers long. And we studied this project about 1 month after the earthquake. Actually, we wanted to go earlier if we could, but this was the best we could do because, as I said, we didn't have a direct damage by the tsunami, but the tsunami collapsed everything, the supply chain, so to speak. So we didn't have anything, any necessary things, such as gasoline to drive a car, or for the first week, we didn't have food to eat. And anyway, the one characteristic with the project is we periodically update our data, our archive. So we did this every 3 months in the first year, and now we are doing this every 6 months. And as a result, the data we have collected amounts to 40 terabytes, or equivalently 1 billion images. me show an example. And actually, the image data that are collected is just a set of still images, but it's convenient to show as a video. But please note that the temporal access doesn't mean anything in this video. This is one of the typical twisted city in this area. As you can see, a lot of buildings are damaged, and the surface of the asphalt was scraped off by the tsunami, and there was obviously some iron because tsunami brought oil from somewhere. Yes, so why we're doing this? Of course, our first objective is to record these damages. I think it is useful for education, civil engineering, and business application purposes. And let me show another example which demonstrates the usefulness of data as a damage record. This is another area. In this case, this is not a residential area. The road runs parallel to the coastline. And from here, this road climbs up a mountain. So did this car. As you can see, there is a trace of tsunami. And actually, on the left side of this road, there should have been guardrails, but they are removed. And the car climb up, still there's a trace. And now you see the guardrail still intact. And how high is this place? According to our GPS data, this is about 38 meters above the sea level. So actually, the tsunami did reach this height. And we do not necessarily just record the damages, but also we want to record everything, recoveries from these damages. That's why we do this periodical acquisition of data, now 3 to 6 months apart. By doing this, we have a set of images like this, not spatial sequence, but temporal sequence we have. And to show you the concept of how our data like, I want to show you the Street View like image viewer we have built. And actually, if you use Google Map, it gives you a lot of constraints, so we use an OpenStreetMap to with our own one. Also, this is interface. You can see these color lines indicate the trajectory we run. images suffices if you know what you are looking for. However, what if you do not know what you are looking for? For example, damages are different cities to cities. So are the recoveries from the damages. Let me show an example. This is one of the largest cities in this area, Kamachi. One month after the quake. As you can see, there are a lot of debris along the street, but most of the buildings retain their shapes. So the damages of this city is relatively minor. Damages are relatively minor. Maybe it is not the right choice of words because there are a lot of people died here too. But because of this minor damage, this city, just 1 year later the quake, has already started the reconstruction process. As you can see, the main buildings are now reconstructed. Some of them are still left untouched, but as you can see, there are a lot of cars running on the road and people working in the city. So this city is alive. However, things are completely different for nearby city, Takayuki. This is one of the cities that has the most severe damages 1 month after the quake. So before the tsunami came, there are a lot of buildings along the street. There are full buildings in this plain around. But tsunami removed most of the buildings, and as you can see, there's almost nothing. And because of this severe damage, as far as I know, it hasn't yet determined how to use this land. I think this is 1.5 years after the quake. Nothing has started. There's no people, no car, nothing, and except for some people gathering for some religious ceremony. And yes, it is so deserted that it is overflown with a lot of weeds, as you can see. And actually, this summer we went to the city. We saw a lot of birds having gone somewhere, and I saw even endangered species of a deer walking in the former main street of this city. So it looked like a nature park or something. Anyway, so different damages, different recoveries. So one thing came to my mind is, can we quantify and visualize this kind of thing from the data, such as extent of the damages or pace of recoveries? And I think we could do it by using computer vision, or we consider a new program that we call for image and city modeling, which is use images like ours to model how a city changes its structure, as shown here. So this type of program has not been studied in our community that much. So we needed to study this program to achieve these goals. And actually, three-dimensional model of seeing, creating three-dimensional model of seeing from images has been well studied for years in computer vision community. Actually, it's not that difficult to obtain this type of three-dimensional structure from the images of ours, and it's based on the multi-view geometry. It's based on the multi-view geometry, and we can have three-dimensional structure, although it is just a point cloud of the feature point, and as well as the trajectory of the cameras. And the first problem we consider is detecting structural changes of the scene. Here we use two image sequences captured at two different point times. From these two image sequences, what we want to do is detect changes of the scene. So what we did is to perform structural motion for each image sequence to get three-dimensional shapes. And then we register these two three-dimensional reconstruction. By illustration, I mean represent two three-dimensional model in a single coordinate system. compare these images to detect changes. And here, we are interested in detecting three-dimensional structural change, not two-dimensional change. So my way of doing this is, recover the syntax densely, say using a match view stereo or something like that. Then compare the two densely recovered depths to detect changes. However, it's still not an easy problem. It is not easy to recover dense depth shape from the images, particularly in the case of these images captured by ground vehicle. And so what we did is not to estimate explicitly estimate the depth, but focused on estimation of the whether the syntax changes or not at each image pixel. So we estimate not the continuous depth, but just a binary variable of the possibility of changes of the scene structure at each image pixel. Let me show example that this shows the point clouds recovered from two different image sequences, and the color indicates which image sequence each point belongs to. The yellow points indicate the points are shared by the two different images, and red is the first one, and cyan is the second one, I guess. And after registering these two different reconstruction, we know the camera poses in a single coordinate system, so we can compare these two images to detect structural changes. That's what we are doing here. And this is the final example, final result. We can see the 1 month after the fact, there are a lot of debris on the road. It is they are quickly removed by recovery operation just 3 months after this, and our algorithm can detect those removed debris. And the next goal is what I want to do is quantify the amount of those debris and how we are doing continue this research. And let me show you another example of study that we are doing. It is we want to detect the existence of each building that mentioned on map. So in this case, we use a map of buildings that was created before the flood came. So in this case, we use a single image sequence and map and GPS trajectory. And what we are doing is perform structural promotion for this image sequence to get point clouds. And what we do is compare these point clouds against this city map to detect whether each building exists or not. But there is a technical challenge, which is this registration part. In this case, we need to register map and the structure promotion and GPS data. However, the technical challenge is actually the aspect of the large movement of almost 2 to 3 meters. This demonstrates the movement. So therefore, let's say GPS data cannot match the map created before the aspect. So we need somehow register these different sources of data in a single coordinate. For example, we confine the camera trajectory within the road described by the map. Using that sort of information, we somehow register this data to estimate the existence of each building. This shows an example. This shows the map before the tsunami came. So there are all the buildings exist. And then tsunami came, and after 3 months later, tsunami removed most of the buildings, also the recovery operations, also removed some of the buildings. And a few months later, more buildings are removed. And finally, we are now sharing this result in a difficult situation because this type of panorama, it is theoretically impossible to show a single aspect ratio. If there is a depth varies significantly, then the weighted panorama looks like this, you can see. So in order to deal with this difficulty, what we did is to focus on two object structure. One is the facade of the building facing to the target street, and the second is the ground surface. The other structures, we blur them to have a natural appearance. And if you simply stitch the multiple image, you will have a mesh like this. And definitely this is something, funny thing happened here. And this is the final result we get. We blur every unnecessary thing. In order to do this, we need to classify each pixel into the facade, ground surface, and other object. And we did actually do this by using the MR-based optimization to get result. I'll show some other results. By using this rich panorama, I think it's it's easier to get some concept of the size of the damage of each street. And I know there are room for improvement. There are some artifacts in the images, and still we are studying how to do these artifacts. And also, we tested another type of user interface, smartphone-based augmented reality, that makes user be able to see how the street looks like previously. So just show the image of the view. So the user uses the smartphone in this way, and through this smartphone, he can see how the street looks like previously, or he can put some information extracted from the images by our method, let's say for image modeling method, on this display page. And I think there could be many other ways of using computer vision techniques for our image data. For another candidate would be image recognition. And actually, how we are doing is location recognition for photograph. Because there are a lot of photographs of the city before tsunami came. There are photographs of beautiful cities, and then reporting beautiful cities. However, there are so many photographs, and maybe most of them are captured in the past. For example, it is captured by classical camera, so there are no GPS data attached. So it is necessary to recognize where the photographs were captured. And in order to do that, the image retrieval line technique can be used. Actually, it is for location recognition. But in our case, it is much more difficult, much harder, because in our case, the image database is completely different from the appearance before the sun came. So anyway, we are doing some research in this direction. Okay, so just no go back to my talk. I just explained what we are doing, and I think our project continues in two ways. One is, as I said, we are going to continue this update of 3D images. Until the full recovery is achieved, I hope it will be soon, but I guess maybe 10 years from now. And also in parallel with this image acquisition, we continue the development of all sorts of methods for quantifying, visualizing, hidden some information inside this image data. One candidate is for image and city modeling. And that is, thank you.
Any questions from the audience?
So, So are there other things that folks like us at Microsoft could actually help with this? Because there's other work that we've done on image processing, both with the aerial photography, which would be a great overlay as a time series in conjunction with the street side panorama, but also some of the other previous work that's been done on the street slide kind of view, the panorama to make it easier, along with some the photosynth work and some of the new work going on as well. Because I think that you're absolutely right, the 4D connection of the time recovery, mapping it then with the social and government data on what was put in for reconstruction would be a very, give you a big picture of actually how the reconstruction is actually happening.